This is the last part of the electrolysis tutorials, and over here we're going to be dealing with the last part of chapter, which is a study of a few examples of electrolysis. Now honestly, over here there's not much to learn for you. The main part of the chapter is understanding how electrolysis takes place in the first place, and also the electrochemical series. How do you decide which ion goes first? So here we're just going to apply that. I can't teach you much really. It's all about you understanding, and but still we're just going to go ahead with a few examples. First one is the electrolysis of acidulated water. Now you would have studied under bonding. This is the structure of H2O, covalent bond over here. So you can see clearly that it's two atoms of hydrogen, one atom of oxygen to make up one molecule over here. Now, if I ask you, are there any free ions over here that can conduct electricity? The answer would be no. You can see there's no H plus or OH minus or anything like that. And we studied in the first part of electrolysis that in order to conduct electricity, your electrolyte needs to have these free ions. It doesn't matter whether it's plus, minus, H, OH, SO4, or Na plus, doesn't matter. As long as you have them, they'll conduct electricity. And if they do that, it's an electrolyte. So you can see clearly that H2O on its own, and by on its own I mean just pure water, 100% pure water, distilled water is another term for it, will be a non-electrolyte. So that explains why we put it under non-electrolyte in the last tutorial. So this will not conduct electricity. So if you put distilled pure water as your electrolyte and have a cathode anode pass electricity, you'll see nothing happening at all. But as soon as you add an acid like H2SO4 here, what H2SO4 does is it breaks these and releases free ions. And releases free ions. Which ones? These ones. You don't need to go into how does it do that. You can look at your books more. I'm not going to go into that. But you should just know that acidulated water is called. Pretty obvious why, because this is an acid, this is water, so acidulated water. So now we're just going to do the reaction for this. Now imagine your electrolytic cell like this. You have the cathode, you have the anode here. I'm not drawing the whole circuit. It's the same as the last tutorial, nothing changes here. Now, you know that this has been dissociated into H plus OH minus. H2SO4 will also get dissociated into H plus, and your anion will be different. It will be an SO4 minus, or rather, it will be a 2 minus. So, I could write 2 minus here. So, just imagine that in this cell over here, you have all these ions just swimming around. So, I'm going to do that with a different color. Okay, so you have H plus. You have an H plus from the water one. You have an H plus from H2SO4. So you have two H pluses here. And I'm going to do cations in a different color. So you have OH minus as one cation, and the other one is SO4 2 minus. Right, so I'm just drawing one for each because honestly I don't have space. But of course there'll be thousands of these just swimming around in the cell over here. So as you just learned the electrochemical series, you can tell which cation will get dissociated at the cathode and which anion out of the two will get dissociated at the anode. So let's take the cathode first. You have H plus and you have an H plus. So it's not rocket science which one will get dissociated. It will not surprisingly be H plus. So, and this is just a no-brainer here, but now you look at OH minus and SO4 2 minus. Now here there's a bit of competition. Now if you remember from the electrochemical series, OH is actually right at the top It's the first one actually. And on the other hand, SO4 is right at the bottom. It's the sixth. Now, if you remember, in when you talk about anions like these, the one higher in the series is discharged. The one higher over here is clearly the OH minus. So the OH minus will get discharged. So we can write the two reactions, one at the cathode, one at the anode. At the cathode, this H plus will gain one electron, become an H. Now this happens to several H plus cations, so eventually you'll have loads of these just H atoms swimming around. So what they do is combine. You would have done this under bonding as well. And H2, it's a covalent bond, so that both of them gain stability. Now the OH minus ions, uh, on the other hand, they actually lose one electron because they're anions, so they become just OH here. And then the same logic, this is not stable by itself, so what we'll do is that four of these will come and they'll make two water molecules, H2O. At the same time, they're going to release oxygen. You can see the balancing. And in fact, I'd suggest that you actually learn this because you're going to come across this reaction very often. So this is the total reaction that's going to happen. So you can see what's going to happen at the cathode. At the cathode, you're going to have H plus getting discharged, but at the same time, half of the H plus will not get discharged. I'm going to draw another diagram here. This is cathode. This is the anode. So over here, let's just make a few H2s here, just signifying that the gas has been released. But you're still going to have a few H plus here who haven't been discharged. At the same time here, you'll have the OH minuses getting discharged. What they do is release O2. They're releasing O2 into the air and they're producing H2O. Now H2O being a liquid here will just fall down in the anode here and it'll come back. I'm gonna draw the liquid here. So this comes back over here as H2O. It drops back into the liquid solution. So you have H plus, you have H2O, and let's not forget you have this sulfate ion which has not been discharged. So you have this over here as well. I'm going to write SO4 minus because I can't write 2 over there, but it is 2. So here you can see that this will combine. The both ions over here, one is cation, one is anion, and you know that they form H2SO4 over here. So it's obvious that they'll form sulfuric acid. And also keep in mind that the H plus that hasn't been discharged is just half the total number. So if you look at it, you're back to this really. You had H plus over here, you had SO4 2 minus over here, and the same thing's happening here, except you're reversing this and forming back the H2SO4. So what's happening is that the total amount, the total weight of H2SO4 throughout the whole electrolysis remains constant. That's a very important point. I'll tell you why a bit later. And also, it's colorless, so you're not going to see any color change as such. And over here, of course, another observation would be that the H2 and the O2s come out. You can detect them via the usual methods, which you'll do under analytical chemistry. So you can see that, I don't know if you know already, but you know what a catalyst is. It's basically any substance that speeds up or just affects the speed of a reaction without getting involved itself. So So H2SO4 remains unchanged. The H2SO4 you have over here at the end is equal to the H2SO4 you have over here. So you compare that to the definition of a catalyst. Catalyst also remains unchanged throughout the whole reaction. And also look at the reason in the first place why did we add the H2SO4. That's only because the H2O molecule that's distilled pure water on its own cannot be electrolyzed, I guess. Yeah, you can't basically carry out electrolysis on it. So as soon as you add the H2SO4, the whole reaction takes place. So in a way, it's speeding it up. It's affecting the rate of the chemical reaction, H2SO4. So we can write here H2SO4 speeds up, and it's unchanged throughout, and that matches the definition of a catalyst. So this particular example of electrolysis, acidulated water, is also called catalysis. So you can see it's just combining catalysts and electrolysis. And the reason is very important because it's often asked in those little 1 mark give reason questions. So I think this is one of the most important examples, and also it gives you the reason why we put distilled water under non-electrolytes. Now I'm out of time in this one, so I'm going to carry on with one or two more examples in the next video.